Alright everybody, welcome to this video on lesson 8.2 to 8.3, which is going to be talking about the factor theorem and graphing polynomial functions. Okay, so the first thing that we're going to talk about is what we did in class last time. So in class, what we did was we talked about what does it mean for a polynomial to have a factor, and what is a factor considered. So first we talked about the number 12. I can rewrite 12 in terms of its factors. That could be 1 times 12, or it could be 3 times 4. Either way, those are two different sets of factors, but they're still factors. They're two numbers that multiply to give you 12. So if we just look at the 3 times 4 example, I can rewrite this as 12 divided by 3 equal to 4. That means 3 goes evenly into 12 with no remainder, so my remainder is 0. Okay, now if I switch 4 and 3, I will also get a remainder of 0. So that's another way to think about it. If we have a factor of a number, then the remainder is 0. So I can apply this same concept when I talk about polynomial functions. If I have a factor of a polynomial function, or just any polynomial, my remainder will be 0 when I divide it. So let's see if this works. So if I take x cubed plus 2x squared minus 13x plus 10, and I want to see if x plus 5 is a factor. Okay? So is this a factor? Alright? So that's what we want to find. So to do this, we're going to use synthetic division. Now because we're doing synthetic division, I take the opposite of my a value. So the opposite of positive 5 would be negative 5. And that goes in my little box. Next, I write the coefficients for each of my terms in my polynomial function, or equation. So I have 1, 2, negative 13, and 10. Now the first step is we bring down the 1. Then I multiply by the negative 5, so this gives me negative 5, and I rewrite it underneath the 2. Next, I add, which gives me negative 3. And I repeat the process. So negative 5 times negative 3 is positive 15. Adding, I get positive 2. Multiply negative 5 and 2, I get negative 10. Add, I get 0. What the last number represents is your remainder. So since I have a 0 remainder, that means x plus 5 is a factor. Okay? So that's basically what we were exploring when we talked about the factor theorem. Okay? The factor theorem says exactly this. If you have a polynomial, p of x, you could say a factor of a polynomial p of x, well, I should say a factor x minus a of a polynomial p of x will have a remainder of 0. Will satisfy by satisfying the following: f of a equal to 0. Okay? So this is actually a bit of information for the information section. But we can continue on in the exploration. So that's kind of what we talked about in the factor theorem. The next thing we talked about was what does it mean to be a 0? Well, we looked at the graph of some equations here. So if I were to look at the graph of x cubed, let's say, okay, or of the last function from the example that I showed you here. So if I look at, let me just copy this real quick. If I looked at this graph of this equation, let me put this in my calculator real quick. So we have x to the third power plus 2x squared minus 13x plus 10. Okay, and I graph that. It kind of takes on the following graph. So here's my xy axis. So I'm going to graph this real quick and kind of give you an idea of, so I'm going to be going by 2's here. And by 1's on the x-axis. Excuse me. Okay, so if I were to graph this function here, x cubed plus 2x squared minus 13x plus 10, I would see that my graph follows something like this. Let's see here. It's going to go up really high, really fast. So much so that I can't even see it. It goes off the graph. Okay? It actually goes off the graph. It doesn't go off the graph, but it comes back down. It goes off until 40 on the y. So at about -3, we're all the way up at positive 40 in the y. But by the time we get back down to x equal to 0, we're back down here at 10. So I'm going to make it just kind of pretend that it kind of goes like this way up high. And then it comes back down, and at 1, it goes like this, and then it comes back up. And there we go. Okay, so there's my 5 there. I forgot to put my 5. So that's kind of what the graph of this looks like. And it continues on down negatively. So the real zeros are if you notice, where it crosses the x-axis. So it's the location of the real zero is where it crosses x-axis. And you'll notice one of my real zeros is right here at -5. And that happened to be the same as my factor for x plus 5. So when we say real zeros here, we are actually talking about the factors of my equation, of my polynomial equation. So when I say real zeros, that's basically talking about exactly what you think of, where it crosses the x-axis, and just in terms of the factors, they're the same exact thing. So when you hear those two phrases, they mean the same thing. And we'll talk more about this in a later section. Okay, so on to the major information portion of tonight's video. So we've talked about this before, but I need to review some end behavior rules for polynomial functions. Okay, so end behavior is exactly what it sounds like. It's what's happening towards the end of the polynomial function. So if your degree of your function is even, this is talking about if we have an even or an odd function. If I'm going up on the left and up on the right, then I'm going to have a leading coefficient that's positive. If I'm going down on the left and down on the right, then my leading coefficient is negative. Okay, I'm going to switch to cursive. It just flows a lot easier with my stylus. If my degree of my function is odd, then that means if I'm going down on the left, I'm going to be going up on the right-hand side of my function. That would be if my leading coefficient is also positive. So if you have an odd degree, so like the last example where we had x cubed, okay, the degree of the function is odd, and the leading coefficient was +1. You'll notice the graph goes down on the left and up on the right. And look, it follows that pattern. Down on the left, up on the right. So if you switch the leading coefficient, so your leading coefficient is negative, you can probably make a pretty good guess that it's going to go up on the left and down as you go towards the right. Okay, so that's end behavior of polynomial functions. Okay, so next I want to talk a little bit more about real zeros. Okay, if you look at the degree of the polynomial function, that will tell you how many zeros you're going to have. So the degree of the polynomial function is the same as the maximum number of zeros. Ooh. Okay, so let's say we have x cubed plus 2x as my function. My max number of zeros is 3 because the degree is the same. Another thing about real zeros is the zero of a function is the point at which the graph intersects the x-axis. So again, going back to this equation, my graph intersected the x-axis at -5, +1, and +2. Those are considered real zeros. Okay? Another thing about real zeros, when you're looking at the graph, you look at when it crosses the x-axis or touches. So when I say where the x-axis crosses or touches the x-axis, so I should say where the graph crosses or touches the x-axis. Okay? So that's what it means to be a real zero in terms of the graph. Okay? Next, we need to talk about the location principle. Okay, the location principle basically talks about looking at two different locations on a graph and noticing that somewhere between these 2 points there will be a 0 on the graph. So if I have a polynomial function, f of x, okay, and I have two numbers, a and b. Okay, if f of a is less than 0, that means the y value that I get out of the function, when I substitute in a, is a negative number, and f of b is greater than 0, okay, that means I substitute in b into my function and I get a positive number, then that means there's guaranteed to be 1 0 between a and b. Okay? And I'll show you an example of this. That's the location principle. Think about it in terms of the graph. If I have a graph that goes like this, okay? Let's say here's A, here's B. Okay? Actually, I don't want to do that A there. Actually, no, I do. I do want to do that. Okay, so let's say my graph goes like this instead. I'm messing up my graph here. Okay? You'll notice going down here, here's f of A. Okay? That's f of A. If I substitute in A to f of x, this is my y value for that. That's going to be f of A. If I substitute in B, here's my y value, and that's going to be at f of B. Okay? Since I have a negative number here at A and a positive number here for the y at B, that means somewhere between these two numbers I have a 0. That's all that's saying, is somewhere between there's got to be a 0. Okay? And I'll show you an example of this, how we use it practically. Next, we're going to talk about maximum and minimum points. Okay? A maximum or minimum point is actually referred to as a relative maximum or a relative minimum. Okay? A relative maximum is the highest point in a section of the graph or a portion of the graph. And it then follows that a relative minimum is the lowest point in a section of the graph or a portion of the graph. Okay? Now the two of these together, if you take all the relative maximum and minimums, we call these extrema, because they are on the extreme ends of the graph, or of the y values of the graph. These are all your relative maximum and minimum. Okay? Now, another way to think of this, guys, is we call these the turning points. So if you think of where the graph turns, if we go back to this example here, one more slide, I hope. There we go. If we go back to this example, the turning points are your maximum and your minima. So those two turning points there, those are my max and min. Okay, so maximum and minimum, your turning points. Alright, that's pretty much all the information for today. Let's look at some examples. I know we're getting close on time here, so I'll try and do these pretty quickly. So, I'm going to take a picture of the first problem. Okay, so I'm going to make this a little smaller so it can fit inside here. There we go. There it is. Okay, so the first example is determine whether the graph represents an odd degree polynomial or an even degree polynomial. Then state the number of real zeros. So you'll notice we go down on the left and up on the right. Since we're going different directions on the end, we know it's going to be odd. Okay? And then we just need to figure out if how many real numbers zeros there are. Well, I only cross the x-axis once at that point right there. So there is one real zero. And that's all there is for that question. So your next example, let me take another picture real quick. Okay, so this next question says determine the consecutive integer values of x, should be of here, between which each real zero of f of x equal to 2x to the fourth minus x cubed minus 5 is located. Then draw the graph. Okay, so to do this, you're going to make a table of values. So we have f of x equal to 2x to the fourth minus x cubed minus 5. Okay, so we're going to make just a big old table of values, your x value and your y value, or your f of x. Okay, and you're going to just choose a whole bunch of them and do them in order. And the reason you want to do them in order is because what you're going to do is you're going to find out where the graph becomes negative or positive. Okay, and so I'm going to put this in my calculator right now and just kind of figure out what the table is going to be. So I have 2x to the fourth minus x to the third minus 5. Okay, so if I graph this, my equation gives me a table. So let's say if it's negative 3, I'm at positive 184. Negative 2 would give me positive 35. Negative 1 gives me negative 2. 0 gives me negative 5. 1 gives me negative 4. 2 gives me 19. And 3 gives me 130. Okay, so where we really want to pay attention is what's happening from here to here and from here to here. Somewhere between negative 2 and negative 1, I switch from positive to negative, so I'm going downward, right? And somewhere I switch from positive to negative, so somewhere between negative 2 and negative 1, there is a 0. Okay, that means I cross the x-axis somewhere between negative 1 and negative 2. And from between 1 and positive 2, I'm going up, right? Because I go from a negative to a positive again. So somewhere between negative 2 and negative 1, there's a 0. And somewhere between positive 1 and positive 2, there is a 0. So if you were to graph this, you would have your graph somewhere between negative 1 and negative 2. It doesn't really matter where. And positive 1 and positive 2, there's a 0. So your graph would go something like this. Okay? Now it could curve up even more like that. Like this. But what matters here is these 2 points. Somewhere between 1 and 2, and somewhere between negative 2 and negative 1, my graph crosses the x-axis. That's all that the location principle is talking about. And my last example for tonight. Here's the problem. Okay. Ooh, kind of a bad picture. Too dark, isn't it? Let's take that one more time. That looks better. Okay, the question says graph f of x equal to x cubed plus 6x squared minus 3 and estimate the x coordinates at which the relative maxima and minima occur. Okay, so we have f of x equals x to the third plus 6x squared minus 3. Okay, so the easiest way to graph this, if you don't have a graphing calculator, which you won't have on the CST, the easiest way to graph these is to make a table. Okay, so you're going to have x and y values. So again, start out giving yourself a lot of values to find. Okay, this will help you in guessing or determining I'm blanking right now. The shape of the graph and where the relative maxima and minima occur. Okay? So, if x is -3, I put this in my calculator or I figure it out by multiplying it out. And let's see, I get x to the third plus 6x squared minus 3. So when I put this in when I work this out, I'm going to get positive 24 here. -2 is going to give me positive 13. -1 gives me 2. 0 gives me -3. 1 gives me 4. 2 gives me 29. And 3 gives me 78. Now, one thing you would want to figure out is if this changes, you'll notice that the degree here, the degree is 3. Okay? So that means I turn, or I have a max amount of turns 3 times. I have a max amount of 3 turns. I don't have to turn that many times, but most likely it will. And then I also have a max amount of 3 zeros. I already know from here to here, from 2 to -3, there's a 0 there. Okay, so I should probably go further down. It looks like as I go further up, as I go further up in the x, I'm gonna go up in the y. So we should probably find out what, if x is smaller, what's gonna happen. So if x is -4, I get positive 29, so I'm getting bigger. If x is -5, I get 22, I've gotten smaller. Okay? And then if x is -6, I'm at -3. And actually, I'll keep going smaller. Okay, so if I were to graph this, what you would do is you can just plot these points. So if x is 0, we're at -3. Okay, if x is 1, we're at +4. So actually, I'm just going to graph by first drawing my x-axis, and I'm going to go by 1s on the x-axis. And actually, I'm going to change this value here on the y-axis. I'm going to go, let's see, I go all the way up to 78 when I hit 3, so I'm going to change it so that I'm going to go by 4s. So the second one is 8, then 16, then 20, then 28, okay? Oh wait, not 28. This will be 24, and this will be 32, okay? And then going negative, I'm at -4 or -8 here, then -16 here, okay? And that's probably good. So when I graph this, oops, that's not -4 and -8, that's -2 and -4. When I graph this, it's going to look a little different than it would be on a calculator that can give you a good square value table, or graph, but it should look relatively close to what the graph should look like. So at -3, we're at +24. So I go over to -3 up to 24. If I'm at -4, I'm at +29. I'm going to erase a little bit of what I have here. +29 is going to be a little bit more than, probably right about there. And -5, I drop back down to 22, even lower than 24. And -6, I drop all the way down to -3, so I'm probably going to be right about here. A little less than 4. Okay? And then I have -2, I'm at 13, which is a little less or a little more than 12. And -1, I'm at +2, so I'm going to be almost right about there. And then at +1, I'm at 4, or at 0, I'm at -3, so I'm going to be a little less than 4. Again, 1, I'm at +4, so I'm right here. 2, I'm at 29, so I'm going to be a little bit more than 28 here. And actually, this one over here needs to go away as well and move up a little bit. Okay, and then +3, I'm all the way up at 78, and so I'm just going to stop there. So now my next thing I need to do is graph a smooth curve and put arrows on the end. Okay, so now that you've graphed that, we can look at the relative maximum and the relative minimum. You can also tell this from the table, but it's so much easier to see that the graph is going a certain direction, or is peaking or valleying, if you say, at certain points. So you'll notice at x equal to -4, I'm at +29, and at x equal to 0, I'm at -3. Those are the two lowest, the two extreme points. Okay, so at x equal to -4, comma 29, that's my first maximum. That's a relative maximum. And it's a relative maximum because there could be another maximum somewhere else. It's not the biggest number, it's just the biggest number in this area of the graph. And then I have, at this point, 0, -3, I have a relative minimum. Okay, so that's pretty much all you have to do for these examples. Okay, so here's your multiple choice question. Approximate the real zero of f of x equal to x cubed plus x plus 1 to the nearest tenth. The easiest way to do this, the hint that I would give you is graph it. Graph it to help you find the real zero. And your free response question is, state the maximum number of turns the graph of the function could make. State the number of real zeros. Okay, how many real zeros could it have? Approximate each zero to the nearest tenth. Okay, so this hint, again, is to graph this function. Approximate the relative minima and relative maxima to the nearest tenth. So the hint for this would be to graph and then explain how you find each of the values. Okay, so hope that was enjoyable. Sorry it was a little long, but there you go. See you guys tomorrow.